Hello, ladies and gentlemen. Welcome to the last session of the workshop Dark and Quiet Sky for Society and Science, devoted in this case to radio astronomy. This conference is co-organized by the United Nations Office of the Outer Space Affairs, by the International Astronomical Union, and by the Instituto de Astrofísica de Canarias, with the fundamental support of NOAA Lab, the National Science Foundation National Optical Infrared Astronomy Research Laboratory. The purpose and scope of the workshop is to discuss the impact that recent technological development do have on the environment, like the artificial light at night alarm, and the deployment of a large number of communication satellites on low Earth orbit, which are seriously affecting the business experience of the night sky, the astronomical science, and the biological life. Most importantly, this workshop will produce a number of recommendations aimed at mitigating the negative effects of those technological developments. The recommendations will be brought to the attention of the world policy makers by presenting a report to the United Nations Committee on the Peaceful Uses of the Outer Space, COPUOS, in which more than 90 countries are represented. A draft version of the workshop report has already been prepared by 5 working groups composed by internationally recognized experts, and it can be downloaded from the website. As we have emphasized along this week, you are all invited to contribute with comments and suggestions in preparing the final version of the report. Your contribution is instrumental to make it effective and shared by the largest possible community. And now we start, and it is my pleasure to introduce to you to the Spanish Minister of Science and Innovation, Pedro Duque, who will welcome us on behalf of the government of Spain.
Dear distinguished speakers and participants, I am delighted to welcome you to the final day of the Dark and Quiet Skies Workshop, a joint initiative of the United Nations, Spain, and the International Astronomical Union. I am confident that the conversations and presentations you have shared this week in the various working groups of experts have been very useful in identifying all the possible interferences that endanger the visibility of the night sky in all wavelengths. The night sky, is a precious resource shared by all of humanity. It's our duty to protect and preserve it so that scientists can continue to carry out groundbreaking research, and so that society at large can continue to learn more about the universe we are surrounded by. Spain is strongly committed to preserving the night sky, as we have demonstrated with our protection of the skies over the Canary Islands. The excellent conditions for astronomical observation on these islands merited special protection that the Spanish government implemented by law. Light and radioelectric pollution, as well as flight routes, are all regulated thanks to this unique legislation. Promoting the excellence of astronomical observation conditions has allowed the Canary Islands to become a hub for top-notch scientific research. It is home to some of the most advanced telescopes in the world, such as the Large Canary Island Telescope and the Cherenkov Telescope Array North. The Canary Islands is also, or would also be, an alternative ideal location for the construction of the 30-meter telescope. We can also contribute to protecting the night sky from space itself, through the monitoring of orbiting objects which could pose a collision risk to our satellites. Spain coordinates the European Space Surveillance and Tracking Program, and also, together with France, oversees the Collision Notification Service. Thanks to this real-time collision monitoring, we can avoid the creation of additional space debris that may be harmful to astronomical observation. In these modern days, where constellations of thousands of orbiting objects are launched, this will prove an invaluable asset. Beyond the scientific opportunities, a clear, starry night sky also offers countless cultural and educational opportunities for local communities and entrepreneurs. Protecting the sky facilitates knowledge generation and promotes profitable business initiatives. In Spain, we have proved that this model is successful in the Canary Islands and several other elevated areas far from cities. In conclusion, I hope this week's working sessions have been fruitful. The final document that will be presented in Vienna will reflect the various perspectives and opinions expressed during this week's meetings. Rest assured of the Government of Spain's full support in this important work, with the convictions that it will also lead to the advancement of scientific knowledge. Thank you very much for your participation in the workshop, and I look forward to seeing all of you at next April's conference in La Palma for the formal presentation of the document. Goodbye.
Hello, can everyone hear me? Hi, my name is Harvey List. I'm a radio astronomer, a member of the scientific organizing committee for this meeting, and the moderator of this session on radio astronomy. Can we have the next slide, please? Introductory material that you should need to know. The reports are available and open for comments online until the 16th of October. That's a week from today. You can download them from this URL, and there is a form for submitting comments on the recommendations. Comments on the reports should generally be directed toward the recommendations. You receive these links, and if not, well, okay, so there's another email. May I have the next slide, please? Speakers, those of you who may unmute yourself, please keep your video and your microphones off. Participants, you will not be unmuted during this meeting, but you can chat and especially write questions. If you have questions, please preface them with something like question that will allow us to identify them during the meeting. Thank you. The next slide, please. Well, I would like to personally thank Spain for its great support of radio astronomy. They have a wonderful astronomy infrastructure, as you just heard, for optical astronomy. They have a wonderful radio telescope outside Granada, which you see at the bottom there in snow, and it's in the middle of the ski resort, at which I have spent many, many happy hours. And despite the fact that it's at 10,000 feet, there's a surprising abundance of wildlife. I couldn't find it by images of the fox that comes in the late afternoon to beg food at the cafeteria. But it's never bad to spend an extra night in Madrid on the way out and catch a little bit of music. Next slide, please. So here are the members of the working group. I'm the chair of this working group. I'm a radio astronomer at the National Radio Astronomy Observatory in Charlottesville, Virginia in the US. And I'm the chair of the IUCAF committee that you'll hear a little more about later. The other members of this committee, like myself, are experienced not only in astronomy and the engineering of radio astronomy, but spectrum management. It's a very specialized art. It takes a long time to acclimate it. It takes a great deal of dedication. It's not something that you succeed at by doing casually. So the first other member of this group is Federico De Bruno, who is the spectrum manager for the SKA telescope in the UK. He, unlike the other members of this group, he has actually had his hands on some of the radars that are now in orbit threatening radio astronomy. Next is Michael Lindquist, who is the spectrum manager at Chalmers and a member of the that functions within the CEBT community to protect radio astronomy. Masatoshi Oishi is the spectrum manager at the National Astronomical Observatory of Japan, and he plays also a dual role in that he's the contact for the satellite interference to the light domain within the nation of Japan. So he plays a dual role spectrum manager, and he's also coordinating with the constellations for their their optical aspects. Adrian Tiplady, who is a staff member and an astronomer at the South African Radio Astronomy Observatory, largely responsible for the workshop that I'll show you later that we had in the spring of this year. Tasso Tsumas, who's the spectrum manager at the Commonwealth Scientific Industrial and Research Organization in Australia. He has a very important role at the ITUR as the chairman of our working party 7D. That's jargon, but it's the working party that is specifically concerned with radio astronomy, and Tasso runs it. Ashley Zauderer from the National Science Foundation at the US, who leads the electromagnetic spectrum management unit at the NSF that looks out for passive science. Lisa Van Zee, a professor of astronomy at Indiana University, who is also, but not representing, the chair of the Committee on Radio Frequencies of the National Committee, the National Academy of Sciences. So that's who put this report together. And so let's go take a look at it. Oh, no, back up one. Okay, there we are. So the report has 5 chapters. We felt it necessary to explain ourselves to a community that is not familiar with radio astronomy, not only in this workshop, but more generally in COPUS that will be receiving the report. So we tried to start with a top to bottom description of radio astronomy. So at the top here, you see Karl Jansky in the field in Holmdel, where radio astronomy was born, right? He was researching the noise to a communication system at low frequencies and noticed a source of interference that seemed to move throughout the day. It was in the same place, but not at the same time, okay? I mean, he got an inclination that it was moving through the sky in space and time, okay? There was a source. Eventually, he realized that this was the sidereal rate he was seeing, right? That it didn't appear at the same time overhead every day, because the sidereal day and the civil day, but which we keep clocks, differ by almost 4 minutes. So the sun moves throughout the sky throughout the day. It's always at overhead at noon, as it were, but as far as what stars you would see when you looked through the sun, okay, this is sort of astrology. It moves through the sky because we move around the sun, and we also revolve around our own axis. So he noticed that it was a cosmic radio source, and indeed he was detecting radio emission in the direction of the center of the galaxy from electrons that have been expelled by dying stars in supernova as they spiral at relativistic speeds through the galaxy's magnetic field. Okay, it's called synchrotron radiation, and it's very sharply peaked to low frequencies. Well, fast forward 30 odd years to another radio instrument at the bottom, which is not very far away actually from the field in which Karl Jansky worked. And this is the horn antenna, the Bell Labs horn antenna at Crawford Hill, designed actually by Art Crawford, who had been Karl Jansky's roommate when they were first young scientists at Bell Labs in the 30s. Jansky died young and did not live to see the fruits of his discovery. But in the early 60s, Bell Labs had hired radio astronomers because radio astronomy had matured to the point that its concern with noise in its own systems, because its signals are so faint, radio astronomy had developed techniques that were of use to communications. And so 2 radio astronomers, Bob Wilson at the left there and Arno Penzias, were hired out of Caltech and Columbia, respectively, and they went to work on this antenna. It was a trade-off. They knew they would have some time to do astronomy, but first they had their functional responsibilities of picking out the noise in this communication system. And of course, they found a source of noise with this antenna that they couldn't explain, and it turned out to be the origin of the universe, right? Okay, so this gigantic instrument, which you can see, was built for communications purposes to have especially low side lobes that we'll talk about later. But this enormous thing would barely resolve the full moon. at the frequency at which Penzias and Wilson used it, okay? Well, of course, it didn't have to have much in the way of resolution because there weren't very many satellites in the sky, were there? Okay, and this was built to study the noise in a satellite communication system. Now, radio astronomy has a very, very long history of involvement with satellites, not only for this reason, but because they have a history of generating interference to radio astronomy in bands where they're not allocated. Specifically, for instance, in the late 70s, the first GPS satellite, and in the early to mid 80s, the first GLONASS satellite for global positioning, they used digital modulation of a carrier with no filtering. And as anyone knows, that just spews radiation all over the electromagnetic spectrum. Okay, I won't bother to show you a picture, but the fact is that they generated large amounts of interference in bands that were at the time used to study the OH molecule, which was a relatively recent discovery and played a much bigger role in astronomy at that time than it does now when we know of 200 molecules in the interstellar medium. So this was not actually settled until, well, these systems were not declared compatible with radio astronomy until 2007 at the ITUR. Even though they started getting their act together, it was not easy. There were prolonged negotiations between their systems and radio astronomy. But in fact, these days, they no longer interfere. But it took a very long time. And there's a great moral in this story. Once an interfering situation exists, it is very, very hard to ameliorate it. Prevention is everything in this game. Now, yesterday you saw an example of something called an iridium flare, right, from the Iridium satellite phone constellation. Iridium has since replaced its constellation with newer satellites that do not generate these flares. But unfortunately, they continue a history of interference with radio astronomy, and you'll see an example of this later. So this has been going on now for over 20 years. Next slide, please. Okay, so this is an outline of the report, which I hope at some point you have a chance to read. It's not been online very long, but it tries to give an introduction to and some feeling for radio astronomy to groups that are not familiar with these concepts, okay? Now, radio astronomy is a relatively new science. Well, of course, Jansky was 90 years ago, but it has produced some amazing discoveries, right? Not starting with, but including as its second Nobel Prize, the discovery of the Big Bang. Other Nobel Prizes have been given for proving that gravitational waves exist. And that was done by timing pulsars. But the fact is that 40 years after that discovery was made, people are now actually observing the gravitational waves that were more or less proved to exist indirectly in the radio by tracking the loss of energy in a system of two pulsars that orbiting each other as they spiral closer together toward an eventual merger, which, you know, maybe someday will also be detected as a gravitational wave. Radio astronomy has the property that because its wavelengths are so long, it penetrates the dust that shrouds much of the optical universe. And this has led to a complementary set of discoveries of how the universe works. Radio astronomy was the first way that you could see across the whole galaxy in any tracer, and the rotation of the galaxy was mapped in a line of hydrogen. Hydrogen is the basic building block of the universe. But we not only observe hydrogen, we observe 200 molecules in the interstellar medium, most of which were discovered at radio wavelengths. In the process of perfecting its technology, radio astronomy has done quite a bit of spin-off. We take quite a bit from radio science and we give back in good measure. Specifically, if you are familiar with the VLA, for instance, which is a telescope in New Mexico, it's an array like the one you see. I should have put it down here using it as an example, but the one at the bottom left is ALMA. it has three arms, oriented not quite north, oriented not quite separated by 120 degrees. There is a satellite in orbit looking down on the Earth, which is a miniature replica of the VLA, using the same techniques to monitor soil moisture and ocean salinity in the same band that radio astronomy uses to detect and observe the H1 line, the hydrogen from the universe. So there's this synergy. Radio astronomy is actually important for technological infrastructure, especially the use of VLBI. Radio astronomy, as we'll see in a moment, has to build very large instruments. Sometimes it can't be done with a single dish because the wavelengths are too long to achieve angular resolution with a single instrument. We need to learn to use them together. Small arrays like ALMA that you see in the lower left are all more or less in one place. And in real time, all of these telescopes are kept in phase so that we know exactly when a wave coming from the cosmos arrives at each one of them. And by comparing the way that wave is received at different places, we can rebuild an image of the emission, okay? Sometimes these telescopes are too big to be connected in real time. And so they are timed with hydrogen masers. And then the electric field is recorded. And then everything is brought together. And because we know exactly when we know when each wave appeared at each telescope, we can beat them against each other to reproduce an imperfect but usable and correctable version of the sky. So in doing this, the international VLBI geodetic effort actually defines the coordinate reference frame that's used to track satellites. The positional accuracy of something like the international geodetic VLBI effort is such that with sufficient access to frequency space, it will be able to chart the motion of continents to a millimeter at the locations where the observations are done, okay? And this is very, very important actually for maintaining the reference frames and for knowing exactly what's happening with the Earth, because the shifts are used for many purposes. Well, okay, so this goes on and on and on. It is a very long report, given the brief time that I have. So let's try to abstract a few things that'll be important to the subsequent discussion. Can we go to the next slide? Okay, so radio waves are the electromagnetic radiation at wavelengths longer than 100 microns. This may be surprising to people, but it's officially defined as extending up to 3 terahertz or wavelengths longer than 100 microns. So many people doing far infrared astronomy are actually radio astronomers. They just don't know it. Radio waves can penetrate opaque dust that shrouds the universe in visible light. And this dust is the same dust that might coagulate around a new star to form another rocky planet like Earth. But cosmic radio waves are very, 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 very faint noise at some frequency, in some direction, perhaps only at that moment. And there is no carrier to lock on, okay? What we detect when we detect a source of cosmic radio waves on the sky, it just means that there's more noise at some frequency at some time in that direction than at other times or moments, okay? We are always comparing the amount of energy that we see in one place with what's supposed to be the background level where we think that there is no radiation, or at least we can explain everything. We're looking for differences, right? We're always looking for differences. And our signals are in fact very, very faint noise. Now, the frequency of this radiation tells you its origin in some cases. The spectral line of hydrogen generally, or a molecule, it's basically like doing gas chromatography. Atoms, molecules have characteristic internal structure that can tell you exactly what they were when you see the radiation at that frequency. But as Lisa will talk about, expansion of the universe displaces signals across the entire radio spectrum, and we have to follow them. The universe is expanding, the galaxy is rotating, things are not fixed. The frequencies at which we observe signals are not those that you would find in the laboratory. And we don't have any choice. If we want to understand the phenomena that create them, we have to go where they go, which means following them in frequency. The last point, I'm not going to belabor right now because it can be quite mind-boggling. Can we go to the next slide? Now, you saw the horn at Bell Labs, and I told you that it had a terrible resolving power, even though it was this gigantic instrument. And that's an artifact of the fact that our wavelengths are very, very long, right? So in order to achieve angular resolution on something that has a long wavelength, you need to have a long diameter. And this long wavelength, creating the need for a large diameter, at some point you are unable to build anymore a telescope of sufficient size to get the angular resolution that you want at that frequency. And so what do? Well, that was what impelled radio astronomers to learn to phase up telescopes in different places and to learn how to image the sky using those telescopes. And that was the Nobel Prize that was granted to Ryle and Hewish in 1974 for developing synthetic aperture radar, where they showed synthetic aperture synthesis, where they showed that by putting telescopes in a fixed location on the ground and observing the same point and letting the sky rotate as the Earth moved, that you could actually resynthesize the image of the sky using those observations. Now, in the report, discussed in great detail is the fact that the noise that we see on the sky is proportional to our system noise, which is what's inherent in our equipment, which we try to make as low as possible, of course, divided by the square root of a product in bandwidth and time. So our sensitivity increases as our bandwidth increases, and it increases as the time increases, as long as everything is steady. If, for instance, your system noise is fluctuating all the time, you will never achieve this theoretical noise. Imagine that you were trying to work and every few minutes at random intervals, you were slapped. How much work would you get done? And then occasionally, maybe an hour later, you were just knocked out and you slumped at your desk for 20 minutes. Well, those are the conditions that threaten radio astronomy and which we're seeking to prevent. So radio astronomy detects cosmic radio waves that are literally billions of times below the signal noise by integrating over long periods of time. Radio astronomy is not a communication service. It's not a radio communication service. We're not detecting things in real time, except only very rarely, okay? The faint signals that we detect are generally steady. Pulsars, of course, there are exceptions of things that are transient. But in terms of this equation, to achieve the ultimate sensitivity of a system, you need things to be steady with a low system noise, and you need access to adequate bandwidth for a sufficiently long period of time. Now, so we detect cosmic radio waves that are billions of times below our system noise, but radio communications are billions of times stronger than cosmic radio waves. Radio communications signals typically exceed our system can exceed our system temperatures. And these are the conditions under which we're trying to detect faint objects. Another surprising thing is that even though we build big antennas, we build very, very big antennas to collect as many photons as we can in the direction that we're pointing, the net gain of every radio antenna is the same. And it's the same as optic antenna with no gain and no resolving power. And this may seem very strange to you. Why do we build such big things if in the end they don't have any advantage? Well, of course they do, right? They allow us to collect as many photons as possible in the direction in which they're pointed. But the fact is that they have response in other directions. And this is the thing that most separates optical from radio astronomy in terms of the current context. The all-sky integral of the area is the same as that of an isotropic radiator, lambda squared over 4 pi. And okay, let me give a little lesson for this, right? An isotropic radiator, what is it? This is the theoretical area of an isotropic radiator. What is an isotropic radiator good for? Well, it's the antenna in your cell phone, right? Your cell phone has no idea where the nearest cell tower is. So it always needs to maintain something like an isotropic response so that it can always find a cell phone. I mean, a cell tower, okay? That means that the area of the antenna in your cell phone is limited to this lambda squared over 4 pi. So right now you're probably using a cell phone that's communicating at 700 megahertz and a wavelength of 40 centimeters. So 40 squared over 4 pi, that's 100 square centimeters. That's sort of the area of your cell phone. Okay, but for 5G, they're talking about using frequencies, let's say 50 gigahertz. That's 70 times higher. The cell phone working at 70 gigahertz still needs an isotropic antenna inside because it doesn't know where its cell towers are. So in order to communicate with the isotropic antenna inside that 50 gigahertz cell phone, either the transmitter has to be 5,000 times stronger, 70 squared, or it has to be 70 times closer, okay? And so what's going to happen is that you are going to need, if you have a 50 gigahertz phone, to communicate with a cell tower that's within 100 meters or so. 5G is going to require an incredible amount of infrastructure if they're going to move to high frequency. So a lot of these lessons from radio astronomy can be extended to the real world. This simple formula that's not too hard to derive in terms of antenna theory is of great utility. But what it implies for radio astronomy is that radio antennas have side lobes where they less strongly see away from where they are pointed. So in the optical case, you could have an ephemeris and you would always know which satellite was moving through your field of view at a given moment, or which it was if it accidentally strayed into your field. But with radio, our radio telescopes will see away from the direction that they're pointed, and radio communications transmitters will transmit in directions where they don't intend to. So you have all of these combinations of the main beam of the telescope and the transmitter and the side lobes of the telescope and the transmitter. And it can make it extremely difficult to identify the source of interference. But the fact is that radio antennas, any antenna, communications antennas, radio astronomy antennas, have these side lobes. And if a transmitter is found within about 20 degrees of the direction that the radio telescope is pointed, that signal will be boosted by gain in the telescope. The last point, which is very, very hard to get across to active services and spectrum regulators, is that telescopes do not have the ability to accept good cosmic radio waves and reject bad extraneous ones. It doesn't work that way. At the same time that we are detecting our signals, we are also subject to the interference that's coming from our side lobes. Next slide. So this is a very, very brief summary of radio astronomy. Radio astronomy is a remarkable engine of discovery, and it has practical uses. Although the practice of it may seem esoteric, it has real-world benefits. Coordinate reference frames. The techniques that we've developed for radio astronomy to recover our images are used all over science. They have great, very wide applicability. We work internationally, often of necessity. We not only build observatories using consortia of different nations, we put our telescopes in different nations working at the same time. We need and we build big antennas and antenna arrays, even globally. But even the biggest radio telescope is blind without access to spectrum. No radio antenna is entirely insensitive to radiation arising in directions away from where it is pointed, even behind it. owing to its side lobes. And you know, it seems hard to believe that a radio telescope could respond to something behind it, but the physical phenomenon is that something behind it can still, the radiation from that can still bounce around and appear to have been detected, right? The report talks about the fact that eyeglasses, right? There are faint reflections of what's happening behind you on the surfaces of your eyeglasses, and you can sometimes see them. Well, those are side lobes. Now, our telescopes are sited misanthropically to escape as much interference as possible. We're surrounded by quiet zones, as you'll hear. There's a large cost associated with operating radio telescopes in the remote places that we do. But there's no choice. Radio telescopes must point upward to see the cosmos, and they're going to have to look past radio communication signals that are billions of times stronger than the cosmic waves. And so the game is to try to prevent the interference of these phenomena. Next slide. Now, all this is said, right, in recognition of some facts of life. The investment in ground-based radio astronomy, I'd say these days is, it's something over 2 billion whatevers, 2 billion big whatevers, dollars or euros. You can find $2 billion just in the telescopes in Australia, South Africa, and the ALMA telescope in South America, in Chile. There's relatively little private investment in radio astronomy facilities compared to optical. I mean, optical astronomy benefits greatly from big national facilities, but there is private investment in optical astronomy that's not mirrored in the radio. And in fact, any of several spectacular satellite industry bankruptcies would have funded terrestrial radio astronomy forever. And there'll probably be more of them. Okay, so that's the first talk in a nutshell. I urge anyone who is really interested in this to look at the report. We've tried very hard to try to flesh out these talking points in ways that are intelligible to a technically informed non-astronomer, non-radio astronomer. Okay, I'm also narrating the next part. Regulation of use of the radio spectrum. It's written, it's very well written, I think. I didn't write this part. I appreciate the way it is written. It's subtle. It has a great deal of reference material in it, and they're all linked so that you can pursue these things further. It's arcane, but spectrum is a shared resource for everyone. And the act of sharing has profound implications. For instance, the act of transmitting and receiving in the same frequency, which is necessary, of course, if you're going to receive someone else's signal, implies a sharing of that frequency. But you're not going to trust your use of that frequency unless you believe that it's reliable. So at the same time that the issue of sharing arises, its complement is the protection of that shared use. And this is the game of spectrum management, allowing everyone in at the same time and to be protected from everyone else. Now, spectrum management and regulation of the radio spectrum began with ships that were sinking at sea, and they had radios that would communicate with other ships of the same line or with their home port, but the ships couldn't talk to each other. They weren't listening for each other, and they didn't have radios that could talk to each other. So people were drowning in the vicinity of other ships, which if they had been alerted could have saved them. And so the International Telegraphic Union, or whatever it was in 1865, enlarged itself to include new uses of the radio spectrum in, I think, 1912 or so, quite a while ago. Maybe sociologists actually study this, but you can see that spectrum management is a kind of radio sociological phenomenon, whereby you have to share the spectrum and at the same time allow private use for individual purposes. The superstructure of this spectrum management has become extremely elaborate. It has its own institutions, mechanisms, etc. A lot has to happen before a transmitter works and interferes with radio astronomy. As you will see in reading this section, frequency is not allocated to people, to companies, or even in most cases to nations, but it's allocated to classes of radio service. And then there are operators within that kind of radio service who share the allocations to that service and have to get along with each other. Allocations are made to these different services, and the radio spectrum is allocated all the way up to 275 gigahertz. There's no allocation between 275 and 3000 gigahertz. But the fact that there's an allocation doesn't mean that the spectrum is used, because until there are rules for using an allocation, it generally lies vacant or fallow, or the only user is a passive service who just listens, like radio astronomy. So you have the services and they have their allocations, but they require rules. And then once the rules have been written to be followed, you can start making frequency assignments to transmitters in places and at certain frequencies. So it's a very, very elaborate chain of processes that are required before a transmitter actually goes into operation. In order for this system to work, you have to have a firm idea of what it means to be compatible and for what it means to protect the use of one allocation from another, or the operation within one allocation from another operator. This is codified at the highest levels in the radio regulations, which is an international treaty that's modified at the World Radio Conference. And radio astronomers are heavily engaged in this. Those who practice this are, it takes time. Can we have the next slide, please? So transmission and reception imply a common frequency use, and they necessitate protection for trust, right? It's called, I think, regulatory certainty in the industry. You want to know before you invest in a system, and that includes a radio astronomy system, that it will be usable. Industry does not invest in things where there is no confidence. Now, communication historically used very narrow bands, and so spectrum rights were very finely sliced. Right? The radio spectrum is proportionately much, much wider than optical in terms of its ratio, from the long wavelengths to the high wavelength end. Optical astronomy roughly is what, 3,000, I always want to talk about in angstroms, 3,000 somethings to 9,000 somethings, angstroms, 300 nanometers to 900 nanometers, something like that, a factor of 3. But the radio astronomy spectrum is regulated roughly over a factor of 100 million. Okay. So proportionately, it's much finer sliced. So mechanisms were created to define rights to use these spectrum slices. They're apportioned among services, not companies. And the practices of these mechanisms is called spectrum management. Spectrum regulators work internationally at ITUR to revise the regulations every 4 years. You may know, if you know somebody who actually does spectrum management at an observatory, you may not think of them as skilled international negotiators, but that's what you do. When you go to Geneva and you work to revise the radio regulations, you're actually negotiating a treaty. At technical level, perhaps, but you're a negotiator. National regulators like FCC or Ofcom in the UK implement the ITUR decisions, but they also influence the way the ITUR works. The work to revise the treaty has an agenda. The agenda probably has of order 100 items on it, of which perhaps 20 involve frequency allocations and compatibility and protection of services. How did these issues rise to the point that they would be considered at an international treaty negotiation session? Well, every work proposes an agenda for the subsequent work. And where do the agenda items come from? They're the issues that are of concern to the individual administrations and regional blocks that come to Geneva to negotiate this. So the upward pressure for things to rise to the point of international consideration comes from individual administrations and regional blocks that are working often in behalf of a particular service that they want to implement, occasionally for radio astronomy. It's a very elaborate process, which is almost fractal, because the entire structure of the ITUR is mirrored in the individual administrations in preparation for this. In the US and in some other countries, the entire structure of the ITUR and its process is mirrored in structure and in activity to be ready for the working party meetings that occur in preparation for the work every 4 years. And these mechanisms require more and more servicing as time goes on. The spectrum is becoming more and more crowded, and radio astronomers have had to negotiate these waters for a very long time. Our use of the spectrum is so different that the ITUR rules for protecting it are still evolving. So next slide. Well, okay. No, back up. Okay, no, next slide. That's it. Okay. In 1960, ERSI, IU, and COSPAR organized what was then ICSU, chartered IUCAF. IUCAF is now the Scientific Committee on Frequency Allocations for Radio Astronomy and Space Science. Back then, it meant something else. Radio astronomers and engineers went to the work equivalent for 4 months in 1959 and 60. And the radio astronomy service was defined as receiving radio waves of cosmic origin. It got a sole allocation at 1400 to 1427 megahertz to the radio astronomy service. This was the original passive band that's now used by other passive services in important global climate measurements and measurements from satellites of the Earth's biosphere. Subsequent effort, which was hard fought, developed protection criteria for radio astronomy with regard to other services and acquired other frequency allocations. Astronomy spectrum managers like Ashley were hired, and Jonathan Williams, who's on the SATCON group, were hired at national science agencies, TASO at CSIRO, and those two at NSF. Radio astronomy within itself created regional bodies to practice radio astronomy spectrum management more locally, and also are members of the ITUR. Michael Lindquist is the chair of the Committee on Radio Astronomy Frequencies that works in the CEBT countries, quite active. Lisa is the chair of CORF at the National Academy of Sciences in the US. And Mazatoshi and Tasso are past chairs of the RAFCAP Committee in Asia Pacific. Another thing that happened, as I pointed out, is that we appointed spectrum managers at observatories large enough to spare the manpower. Most of us divide our time with other activities, and even Ashley and Jonathan at the NSF have other responsibilities besides spectrum management. Next slide. We go where the action is. The sun picture at the upper left is the sunrise over the Gulf of Aqaba, where quite a few of us, spent 4 weeks at work 19. There wasn't a single day when the sessions let out before sunset. That's how I know this is the sunrise picture. And there's a picture of a bunch of us, some of us represented at this meeting. The inner 5 from left to right are me, Mazatoshi, Jonathan Williams, Ashley, and Federico Di Bruno. The two on the outside are Walid Madkur, who's the spectrum manager at the Committee on Radio Astronomy Frequencies in CEPT, and Baltazar Indermüller, who I think I saw registered for today's meeting and is working at CSIRO. Next slide. So right before the world closed down for COVID, we actually managed to run the 5th International IUCAF Spectrum Management School for Radio Astronomy in Stellenbosch, South Africa, a wonderful place, thanks to the magnificent support of Adrian Tiplady and the people at CERO. This was supported by IUCAF and RadioNet. We did not, to encourage third world participation, there were no fees associated. Fifth in a series, which will be repeated. So the point is that we not only practice this, we try to bring up a younger generation of people and engage others through our EPO, because we need people to be involved in this, and it's a huge distraction from an astronomy career. But it requires an enormous amount of dedication. I've been to 5 works now, and this is the first work at which I felt I actually accomplished anything. Now, maybe I'm just a little bit dim, but the methods, the mechanisms are extremely arcane and require dedication. So we're always trying to bring up new people. Okay, I think that's my last slide for spectrum management. Next slide. Okay, so I'm going to hand this over now to Lisa Van Zee, Indiana University, the chair of Corf, who's actually been turning the slides in lieu of my dim computer connection. So Lisa, can I give it over to you now?
Yes, thank you, Harvey. And I do apologize to everyone when my slide advancement didn't quite work. Computer beeps and then slowly it changes. So in my section of the report, we were talking about spectrum protection and the importance of bands that are allocated to radio astronomy, and in very particular, those that are dedicated to passive use only. Just as a reminder, from what Harvey just said, the radio spectrum is shared between a variety of different users, including commercial, government, and science uses. And although the radio spectrum covers from low frequencies up to 3 terahertz, only up to 275 gigahertz is actually allocated. I would like to point out that in the days past, the IAU identified bands for science use below 3 terahertz, and these are really very useful tables, although some of the higher frequency ones may need to be updated based on the beautiful results coming out of ALMA. As the demand for radio frequencies from commercial use, everybody loves their cell phones, that has caused more difficulties for radio astronomy because radio astronomy has been not only using the bands allocated to us, but also taking advantage of the fact that as a passive service, we can utilize any frequency without actually interfering with anyone else. And so if there are bands that are allocated but not used, radio astronomy has been making use of that. So there is an increased need for sharing the spectrum and for coordination between radio astronomy facilities and the government agencies that regulate the use of spectrum. And one of the really prime points, and I think we heard this with the optical community in the last couple of days, that it's really hard to reverse any regulations and to recover spectrum when we are negatively impacted. That pretty much once it's gone, it's gone. It's very, very difficult to get it back. Although there have been some spectacular examples of recovering. But for the most part, if it's gone, it's gone. So Harvey mentioned the radio regulations. There is an international table of frequency allocations that specify primary allocations, which if you are a primary allocation, you are entitled to protection from harmful interference from other services. There are also secondary allocations, which gives you legal standing, but not much protection. And then one of the things that I learned in learning about spectrum management was that footnotes are really important. And in this case, there are 2 very important footnotes to the radio regulations that are important for protecting radio astronomy. 5.340 states that all emissions are prohibited in the following bands. And then it lists several bands that are separated by about octave measures designed specifically to enable both line observations of important spectral lines and continuum observations in order to sample the spectral energy distribution. Radio regulation 5.149 is not as strong. This is your urge to take all practicable steps to protect radio astronomy. But it does have the very important clause stating that emissions from spaceborne or airborne can be particularly serious sources of interference for the radio astronomy service. And that is because we are looking up, and so anything that is flying overhead has the potential for severe interference. So in terms of the allocations to radio astronomy, at the lower frequencies, we have a very tiny fraction of the radio spectrum allocated directly to us. Below 5 gigahertz, we have 1.25% of the spectrum as 5.340. That's the all emissions prohibited, passive use only bands. And then we have some additional allocations, either primary allocations or 5.149 bands that are noted. At the higher frequency end, radio astronomy was allocated a large fraction between 95 and 275 gigahertz. And that is partly because there is so much science to be done there. The molecular lines, there's just such a wealth of information to be gained at those higher frequencies. But radio astronomy was also able to get access because nobody wanted it. There wasn't a lot of commercial development at those higher frequency bands, and so why not let radio astronomy have some use there? And this is where, as technology is developing, there's now, at least in the United States, a huge push to start utilizing, having commercial use above 95 gigahertz. And so we're running into issues where this large allocation for radio astronomy, again, scientifically justified due to all those beautiful molecular bands, is starting to be challenged by commercial applications that want to use that spectrum as well. From a technical standpoint, again, there are no allocations above 275 gigahertz, but radio astronomy's interest in the 275 to 1 terahertz are noted in regulation 5.565. And the radio astronomy interest there is 58% of that band. It's basically all the beautiful atmospheric windows between the strong absorption lines from water and oxygen. So I thought it would be helpful to show an example of a spectrum and how these radio regulations, the allocations, fit into a typical spectrum. So this is L band, that is from 1 to 2 gigahertz. And the black spectrum is observed intensity at the Very Large Array in April of this year. And you can see that there are very strong transmissions, and those are that spectrum that is allocated for commercial use. You can see the satellites in there, as well as a couple other features. And I have highlighted here the narrow bands that are allocated to radio astronomy and color-coded based on the type of allocation. So the reddish bands are ones where we have a primary allocation. The 1400 to 1427 megahertz is 5.340, so that's an all emissions prohibited band. 1610 to 1613 and 1660 to 1670 is a primary allocation to radio astronomy, but it's a 5.149 band. And you can see that even though there's a radio astronomy allocation, that lower part of the OH line emission is right in the satellite piece of the spectrum. And so there's been a long-standing problem where, although radio astronomy is allocated and a primary allocation, so should be protected from other services, that radio astronomy has had strong interference from some satellite systems that I will not name at this moment, but is often a curse word in the radio astronomy community. So even though we have a primary allocation, once the satellites are launched, it can be very, very challenging to get the spectrum back if it turns out that the satellites do not operate as anticipated. In addition to the primary allocations, we have 5.149 bands that are not primary allocations. The 1727 gigahertz is another OH line, and that's a secondary allocation. The 1330 to 1400 is a 5.149 band that does not have a corresponding allocation of any type. And that is designed for redshifted neutral hydrogen. So the 5.149 bands, again, all administrations are urged to take practicable steps to protect radio astronomy, but there isn't necessarily an allocation, and radio astronomy has to stand up for itself. Now, I will also mention here that there's a whole lot of spectrum that doesn't have shaded components, and some of it actually looks pretty clean. And as was mentioned by Harvey, as radio astronomers, we can use the spectrum without interfering with other systems, as long as it doesn't blow out our receivers. And there are scientific reasons to need to use the rest of the spectrum. Okay? So the 5.340 bands are particularly important because they are supposed to be all emissions prohibited. They are critical for calibration. They are critical for sensitive measurements. They're critical for time variable studies where you need to make certain that everything is natural emitters and not human made. But if you're interested in continuum observations, there is benefit to observing a much wider band than just that allocated to radio astronomy. Because as Harvey mentioned, you can increase your signal to noise ratio by using a wider bandwidth. It is also the case that if you are trying to trace neutral hydrogen in the nearby universe, you need not just the 1400 to 1427 megahertz band, but if your galaxies are more distant, then you need to be able to observe at lower frequencies. And if you're trying to do the early universe, then you need to be observing not in L band at all, but actually in much, much lower frequency bands. And so for scientific reasons, radio astronomy would like to have access not just to our narrow bands that are allocated to us, but also to the remainder of the spectrum when feasible. And so one way to obtain access, first of all, is to hope that nobody gets allocated, but that's not realistic. The other way is to make certain that your radio telescopes are sited in locations where you don't expect to have a lot of human emissions. So this is a figure from Australia where they illustrate the use of the radio spectrum as a function, essentially, of population density. So if you site your radio telescope in downtown Sydney, Australia, you're going to have a lot of human-made emissions. If you go out into the outback a bit, you have a lot more frequency bands that are free. And if you go into the really, 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 really desolate outback, you can have almost clean radio spectrum. So when we are figuring where to site our telescopes, it is important to take into account the local population density so that we can take advantage of the fact that even though everybody loves their cell phones, if nobody is there, then maybe the spectrum will be cleaner. So several countries have designated radio quiet zones, even though we don't listen to radio frequencies. The quiet terminology has crept in. So in the United States, we have a National Radio Quiet Zone associated with the Green Bank Observatory, and we have a coordination zone associated with Arecibo Observatory. The Very Large Array does not currently have such a designation. In Australia and in South Africa, there's been a tremendous amount of effort put into protecting the radio astronomy sites where with the quiet zones, you not only have access to the spectrum that is officially allocated to radio astronomy, but you do, again, have the chance to coordinate such that you have access to the spectrum that is not officially, globally allocated to astronomy, but locally you can have access. One of the problems for the radio quiet zones is that almost all of the coordination is based on terrestrial transmissions. You can ask them to site that cell tower back behind that terrain shielding mountain, but anything that's in the sky is going to be problematic. And so there's a long history of geostationary satellites blocking access to the sky in certain locations. We now have the issue of the non-geostationary satellites that are being tossed up in the tens of thousands, which means that multiple satellites will be visible at all times. And there's yet a different idea called a high altitude platform in which you have, instead of being in orbit, you have something that's a high altitude and can transmit to ground stations. And those will also have several stations visible. So most of the quiet zones have coordination agreements, and it is possible to have transmission free times available for geographic areas. But in the era of the mega satellite constellations, these are going to be very difficult, not only to negotiate, but to actually implement as the footprints are likely to include the radio facilities. So we are in challenging times. We do have regulations in place. Radio astronomers are comfortable with the international and domestic process of negotiating regulations, but it will be very, very challenging to implement these over the next several decades. And I'm going to hand this off to Federico. And let me get to his slide. And Federico, let's hear about the risks to radio astronomy.
There, okay. Perfect, thank you, Alicia. Sorry, I was having trouble to unmute. Okay, so I will be talking about the risks for radio astronomy. And in this slide, you can see the table of content of this section in the report. This presentation will be, of course, an extract of this section because of the time. But of course, you can find all the information in the report and much more. Next slide, please. Yeah, thank you. The first thing I would like to do is highlight some of the facts about radio astronomy and radio frequency interference. As Harvey mentioned before, our observations are several orders of magnitude more sensitive than typical communication systems, detecting signals way, way below the system noise. So due to this sensitivity, RAS antennas cannot distinguish basically from intended signals and interference, even when the interference enters the antenna through the side lobes. So radio astronomical observations normally require a large portion of spectrum, as Lisa was saying before, like for example, to be able to follow redshifted spectral lines from extragalactic sources, or to increase sensitivity for continuum observations, for example. But the issue is that most of the time, this extra spectrum is assigned, of course, to other users and normally active users. So the risks that radio astronomy faces due to radio frequency interference are very wide. There's a wide range and can go from damaging a receiver to losing data in a certain frequency range for a certain period of time. Next slide, please. So these are the 6 topics I want you to take you through in this short presentation. First of all, the interference in frequency bands allocated to radio astronomy. Then I would like to talk about the use of the spectrum outside of the radio astronomy bands, then the radio sky in general, then high power radars, GSO satellites and existing NGSO satellites, and finally the new large NGSO constellations or mega constellations. Next slide, please. Okay, so let's start discussing the increasing interference in the radio astronomy protected bands. The protection of these bands is not absolute, meaning that the protection criteria, basically the thresholds that other systems need to respect, are defined for typical parameters of observations in the recommendation ITUR RA769. The Radio Astronomy Service protected bands are constantly under pressure by active services. So RAS receivers are not only sensitive to in-band and adjacent band transmissions, but also to signals with further frequency separation, also known as out-of-band emissions and harmonically related emissions. In the figure there, you can see a representation of this situation, where the light pink band would be the radio astronomy band, and all the other colors would represent other communication systems using the radio frequency spectrum. Of course, this is a representation, but what this is showing is that because the RAS thresholds are so low, the skirts or the out-of-band emissions from very far away signals in radio frequency terms can exceed the protection thresholds. And even sometimes harmonically related signals can enter radio astronomy bands, as you can see there in the example of the blue signal. Furthermore, the radio regulations of the ITU mandate that radio astronomy has to accept 2% of data loss from a single service and up to 5% from the aggregate of services. These definitions are sometimes interpreted in different ways and can lead to difficult situations for radio astronomy. Please click. Thank you. So in some cases, theoretical studies may show compliance, but the real system can behave very differently than expected. And for satellite systems, this is a very important issue because the detection and report of interference does not always translate in automatic remediation. If we think about satellites, the hardware is up in space and it's very difficult to modify, if not impossible. Right? Another tragic example of this is, as Lishi was mentioning before, and Harvey also mentioned it, and anyone having this kind of talks needs to mention it, is radio astronomy's inability to observe in the OH molecule in the 1610.6 to 1613.8 megahertz due to the interference from a satellite constellation that is authorized to operate 4 megahertz above this frequency range. Unfortunately, this has been the case for more than 20 years now, reducing to almost zero the astronomical observations in this protected band. So that you can see in the figure on the left, the radio astronomy protected band, and the figure on the right, the satellite transmissions. Next slide, please. Okay, so let's now move to the use of the radio spectrum outside of the protected bands. And very often observations, as Lizzie was saying, need to be conducted outside of the protected bands due to the characteristics of the signals under observation. And most modern RAS receivers are very wideband, and radio astronomy basically does an opportunistic use of the radio spectrum, because being a passive service that only receives radio waves, it doesn't generate interference. But the advancement of wireless technology keeps increasing the spectrum use all around the protected RAS bands, especially near populated areas, making this opportunistic observation more difficult by the day. You remember this picture from moments ago, showing all sorts of signals right next to the protected bands. Only the satellites are marked in there, but there are other transmissions in there, like, for example, cell phones or other things. So there are many signals out there. And this is basically the reason why many radio astronomy observatories are protected by radio quiet zones, as you saw before. And the cosmic signals can be, so because of these cosmic signals, can be easily buried by these relatively high power transmissions from terrestrial, maritime, aerial, or spaceborne transmitters. And this doesn't only generate data loss. Very strong RFI signals can completely saturate a receiver, sometimes even being outside of the radio astronomy receiver's band. Next slide, please. Okay, so now let's focus on the radio sky. The sky is full of radio sources, most of them beaming radio waves towards the Earth, because they try to communicate with the Earth, of course. And radio astronomers are trying to observe towards and past these transmissions. So for these overhead transmitters, as Lizzie was saying before, terrain shielding is not effective to protect radio astronomy observatories. Aerial or spaceborne transmitters can be seen from huge distances. As some examples, the line of sight distances for airplanes, high altitude platforms, and satellites in LEO orbit, as you can see there, are in the order of 350 kilometers up to 4,000 kilometers. So this basically means that radiation from these systems will reach the radio astronomy antennas from very, very large distances. And the only barrier that is between these transmissions and the radio astronomy antenna is basically the spreading loss of an electromagnetic wave and atmospheric attenuation as a function of frequency. Next slide, please. Now, if we think about a RAS antenna being a very high gain antenna looking upwards, while some very powerful satellite systems are looking downwards, what can happen? Right? As you probably imagine, high power radars are one of the most damaging risks for radio astronomy, even with low probability of occurrence, but if it does happen, it's very dramatic. So synthetic aperture radars, or SARs, can generate signals up to 17 dB or 50 times stronger than the power level that can destroy the first stage of a radio astronomy receiver if beam-to-beam coupling occurs, so if they're both pointing at each other at the same time. With these advancements in small satellite technology, these SAR systems are no longer limited to national space agencies, and now private companies are already deploying these SAR constellations. Radio telescopes must, at all costs, avoid pointing near such satellites when they are mapping the area close to the telescope site. And the ITUR has included the recommendation RS 2066 to mitigate the risk of direct beam-to-beam coupling from SARs working at 9.4 gigahertz as an example of some of the protections that radio astronomy has against very powerful radars. Another example of this is a cloud profiling radar working in 94 gigahertz that can briefly saturate every RAS receiver which it passes, no matter where the RAS antenna is pointing. And it's also worth noting that car radars in 76 to 81 gigahertz are also powerful enough to destroy a receiver at close range. So these close encounters with the car radar are possible in hilly terrains with roads, as found in some observatories. Next slide, please. Okay, so now that we are looking at the radio sky, what about the existing communication satellites in orbit? As we said before, overhead transmissions presents a very challenging situation for radio astronomy. But slow-moving or fixed satellites can be avoided by radio telescopes. Of course, as Lizzie was saying before, these fixed sources generate a blockage on the sky, but can be avoided. Or their effect can be mitigated by post-processing techniques. This is the case, for example, for GSO satellites. And as an example there, you can see in the picture how the existing GSO satellites are seen from the SKA Mid site in South Africa. So also for the case of the existing MEO and LEO satellite constellations, these are now satellites that move in the sky, their transmissions are seen almost 100% of the time through the side lobes of the RAS antenna due to their low sensitivities. Next slide, please. Okay, and last but not least, let's talk about the risks from the new mega constellations. As we all know by now, these are constellations of about 1,000 to 4,000 LEO satellites in their initial deployments, with prospects of getting up to nearly 100,000 satellites. So there are two different aspects of the risks that these constellations present to the radio astronomy service. First, the potential of interference in the protected RAS bands. As I mentioned before, there is some experience about these risks developing into a problem. And second, the effect that they might have outside of the RAS bands. So starting with the risk for RAS bands, the spectrum used by these constellations is located adjacent or close to some important protected RAS bands, and the operators are committed to protect them according to the ITU radio regulations. And this can be seen in the ECC report 271, where this is a report from CEPT in Europe, where operators are showing commitment to mitigate this risk, even by agreeing not to use the immediate adjacent channel to the RAS frequency band. But as we mentioned before, the protection of the RAS bands is subjected to a total data loss of 2% from one system. This data loss is computed across all the sky, resulting in areas that can have larger data losses, especially at the latitudes near the inclination of the orbits. On the top figure there, you can see a snapshot of the Starlink Phase 1 constellation, and on the bottom, there's a picture of the data loss in the sky for the F-spheric telescope taken from the ECC report 271. Next slide, please. Okay, so to finish, let's look at the risks outside of the RAS protected bands. As we said before, RAS receivers are typically broader than the protected radio astronomy bands, and downlink transmissions from these satellites will fall within the operating bandwidth of many RAS receivers. For the second phases of the proposed constellations, thousands of satellites will be always above the horizon, contributing to the receive power through the side lobes of the radio telescopes, but also increasing the probability of strong interference through main beam coupling. In these two figures, you can see the distribution of the satellites around the globe on the top and in the local sky on the bottom. For the bottom image, that is a persistent simulation for 1,000-second steps. The level of radio interference that a radio telescope will receive as aggregation from all the visible satellites is directly related to the power flux density, or the footprint, to use a more colloquial term, that the satellite places over the radio astronomy site. So with thousands of satellites moving rapidly through the sky and being seen as bright sources, radio observations in some frequencies will experience a significant challenge in the future. And now I will pass the controls again to Harvey with the rest of his part. Thank you.
Thank you, Lisa, and thank you, Federico. So the last part of the report, the way forward and what we will do for ourselves and recommendations. So the first part of it is what radio astronomy can and will do by and for itself. Now, we're aware of these risks. The question is, what are we going to do in response to them? Well, of course, we try as hard as we can to identify them. So, of course, we're going to continue to operate in remote locations. We're going to try to have coordination zones. But we're still looking overhead, and we're going to be increasingly in the presence of strong communication signals. In many cases, these strong communication signals will be close to free spectrum in our passband. And the question is, how can we shield ourselves from the slapping effects on our system of the strong signals that are adjacent to those bands which we finally find are free and usable? So we have the problem of increased spectrum occupation by these telecommunication systems, And then we have to learn to identify, to observe in their presence. So can we have the next slide, please? We've made a list for ourselves of all the things that we can do using electronics to make our systems as robust as possible. The goal is to keep the system linear in the presence of strong signals when we find clear spectrum nearby. Our passbands are very broad. In many cases, we're casting a very wide net, looking at parts of the sky, hoping to find emission or signals from parts of the universe whose redshift and frequency we don't actually know. Okay, in some cases, we know the frequency which we want to target, but in other cases, we have a source whose frequency, whose redshift, we don't know. So we have many reasons for continuing to use the broad bandwidths that we use. We haven't yet learned to filter our receivers in ways that don't substantially affect the system temperatures. So we have to make them as robust as possible, leaving the possibility, the likelihood that they're going to be open, at least for a long time. And so the report tries to identify as much of this as possible. We need to build systems with extremely high dynamic range and high time resolution, so that when interference or saturating signals occur, it can be extirpated or remediated with algorithmically. Next slide, please. So we'll continue to do this, but we can't do it on our own. And what's more, we really can't even do it within the present frequency regulation, spectrum regulation regime, because the mandate of spectrum management does not take account of the fact of the need to use the spectrum for science. The spectrum management regime is extremely ecumenical. Okay, it takes in all uses and tries to make them compatible with other uses. But if this continues, it's going to get to the point where there is simply no available spectrum for science, and the loss is not imaginable. What would the universe be like if we didn't know it was there? It's an interesting philosophical question. What would your view of yourself in the universe be like if you didn't know that there were other galaxies or a Big Bang and an origin to the universe? Well, in fact, this and other knowledge is at stake now. So next slide, please. So we've come up with two recommendations, which we hope are possible to implement for satellite systems. Now, I earlier cited the interference that Iridium generates in one band. The Iridium system is a satellite system. They launched about 100 satellites. The original intention was to use 77, that's Iridium. They finally wound up using 66, which is dysprosium, and decided not to rename themselves. But as you learned from the SATCON talk yesterday, with a Leo constellation, somewhere between 5 and 10% of the constellation is visible at any given moment. What you have to realize with a Leo is that although they're occupying 2 pi steradians in the sky, half the sky, they're much closer than the stars. Right? And so you can only see a fraction of the constellation at any time. And that number is typically 5%. For Iridium, it's about 5% at its orbit. So Iridium has been causing this interference with 3 visible satellites at any time from a constellation of 66. The OneWeb constellation is 1 order of magnitude greater in size. And the combination of OneWeb and the initial Starlink constellation is approximately 2 orders of magnitude higher. And the ultimate is 3 orders of magnitude higher. We are going to have to learn somehow to observe in this. And we ask that at least our sites not be illuminated, especially by the radars that are continuously going to be mapping the Earth's surface every hour, practically. One of these companies has this motto, every square meter, every hour, something like this, okay? We ask that our sites and our radio quiet zones not be illuminated with the main beams of these satellites, that they be built and designed with that capability in mind so that it can actually be used. And we ask that they keep their side lobe levels low enough that their indirect illuminations of radio telescopes and quiet zones do not interfere. Because as you've heard, side lobe interference, even though it's less than the main beam, once you get a sufficiently large number of satellites aggregating, that can build up. So in fact, that's it, right? We have a fairly long report. It all boils down to these two sentences, these two recommendations, because you saw in Federico's talk that there's a wide variety of risk to radio astronomy. The known knowns, right? And we're trying to account for them as much as possible. But we think that these two things are really going to be required for us in the future, no matter what we do. And these are the recommendations that we make. So I'd like to thank everyone who's attending. I believe this is the end of the formal radio astronomy presentation, more or less on time, maybe a couple of minutes early, and we can now go to the question section. Thank you.
So good day, morning, afternoon, evening, everyone. My name is Andy Williams. I'm External Relations Officer at the European Southern Observatory, and I'm going to be moderating this question and answer session this evening. So thank you very much to all the presenters for these fascinating presentations, and thanks everyone also for the excellent questions in the chat. And as usual, we have too many that we can cover in this half an hour. So the first question comes from Angel Otarola, and he's asking, is there a measure about the science data losses that are due to radio frequency interference? And we have, to answer this, Harvey List.
Okay, thank you. Well, I wish there were an answer to that, but in fact, we don't know. And we don't know for many reasons. In most cases, the observations are not done synchronously. They're taken over long periods of time. They're given to the PI without any, he looks at them much later. He may or may not report back to us. I would say that in general, a PI does not report back to us any but the most serious cases of interference. And in many cases, what a radio astronomer likes to call interference is not interference in the spectrum management sense of the word. So we just have to live with it, right? It's only the allocations to radio astronomy that are protected. So I gave a two-part answer, right? First is, I don't know. And the second is, I wish I did, but the reporting mechanisms back are very haphazard. I'd say that we only learned of the most serious cases.
Thanks, Harvey. And there's a kind of follow-up question to this, and this is about the typical number of sources lost in a typical observing run, and is there a sort of known rate of losses from other radio observatories in general?
Well, it very much depends on what you're doing. I mean, I've had cases where an astronomer came to me and said, what is this strong interference that's preventing me from seeing a redshifted water maser at Z somewhat less than 1 when I look in this certain direction, okay? And it turned out that he was looking at 12 gigahertz right in the middle of the geosynchronous orbit, where it's very unlikely that you can ever observe interference free. That's a case where the interference could have been avoided if he had been more aware of the fact that his source at that moment in time was behind the geobelt. But it's a relatively common case where a known interferer in the sky is just not recognized by an astronomer. That's it.
Thanks, Harvey. And please stay on, because there's another question for you. And so you mentioned about the 5G satellite links. Is there an estimation of how large in number of satellites that these 5G satellite constellations could actually go, and which radio astronomy facilities are particularly prone to these 5G constellations?
Okay, so it's somewhat of a misnomer to call the constellations 5G. What I meant for 5G was terrestrial infrastructure, right? That was mostly what I was talking about. It turns out that the satellite constellations are going to provide bandwidths, data rates that are comparable to 5G. I think even the initial Starlink constellation provides a data rate that's higher than what most people are getting for 4G. But the answer is that I was specifically discussing terrestrial infrastructure. And believe me, it's coming to a telephone pole near you. Okay, that's it.
Thank you. Okay, so the next question. So this is a question about the main beams of the antenna. So in the case of satellites, the broader the main beam of their transmitters, then the longer they will take to cross the detection beam of any given radio telescope. From that point of view, are there any concerns with respect to the existing LEO satellite constellations and their particular designs, their orbital heights, and the time it takes them to transit over an observatory? And this is a question for Federico.
Yes, thank you, Andy. Certainly, the width of the beam of a satellite, along with its transmitting power and orbital parameters, affect the impact it can have on radio astronomy. To make the answer short, perhaps, the narrower the beams are, the better, because it basically lowers, first of all, the possibility of direct beam-to-beam interference. And at the same time, for radio astronomy, it's better if the antennas have low side lobes at the same time.
Can I make a remark?
Yes, of course.
Well, I mean, the beam width of a communication satellite is determined by what it needs to serve a population on the ground. Right? And as we heard yesterday from Pat Cooper, the lower the elevation and the smaller the beam, the more satellites you need. So it's not clear that you win this way. The point is that a given location on the ground to be served by the satellite system is going to see a certain signal level at all times. And the configuration of the constellation doesn't matter so much as the service level that that constellation needs to provide on the ground for its own purposes. And the only way to avoid this is by having them not illuminate the radio astronomy site. In the absence of a regulation like that, you would see the same signal level all the time from no matter which constellation you were illuminated by.
Thanks, Harvey. So it's a kind of related question. This is from Andy Lawrence. And he asks, are the Starlink satellites already transmitting, or are they just test flying? Have they been seen by radio observatories? And I think we have Federico to answer this.
So yes, as we heard yesterday from Patricia Cooper, the Starlink constellation at this moment is doing beta testing in the US, as far as we know. And there are many observatories that are planning or trying to measure the emissions from these satellites, the transmissions. And as far as I know, I think there was a comment from Pepe there from Spain, that there has been a team from the US, I think it was from the MIT, who did some measurements but it was on the carriers of the satellites and not yet on the full transmissions. So that's something many people is working on, but also because of the stage that the constellation is on, has not been done yet, as far as I know.
Thanks, Federico. So the next question, and this is a very interesting one, again from Angel Otarola. So the radio community successfully managed to protect particular bands for radio astronomy science. Can we use this experience from the radio astronomy community to achieve an international regulatory framework applied to the other bands in visible and infrared? So can we learn from the experience of radio astronomy in the other bands?
Can I answer?
Anyone who, yes, Alvi.
Well, you know, when I began to be involved with the optical astronomy community, I was quite surprised at their lack of formal engagement with organizations like the CIE that set lighting standards. So I don't know exactly what is the likelihood of success, but the first thing you have to do is get engaged, right? There's a joke about the guy who sits on the edge of his bed and he curses God for never winning the lottery. And he does this so often that eventually the heavens open and God speaks to him and says, buy a ticket. So I would say that the first step is to try to organize internally and see where they have to go. And I'm not sure what their motion is in that direction. They'll have to spend a couple of $1 million a year on the manpower that's expended. I mean, for radio astronomy, I'd say that worldwide between the government, NSF, NAOJ, observatories, there are at least 10 people, 10 FTEs, I would say, involved. Something that would be a minimum. So the community has to be ready to bear that expense. They have to do some organization. They'll have to research exactly what they need to do. But for instance, I don't understand why they don't appear at the general assemblies of the CIE to make their case for the color temperature of LEDs. Anyway, I rag on them for this, and I think that they still have yet to take the very first steps. Thank you.
Thanks, Harvey. And I mean, I think as a result of the actions taken from the NSF AAS SATCON conference, which happened earlier this year, and of course, the work that we're doing in this conference, I mean, I think we're starting to take those first steps. We also have a working group that's organized by the Royal Astronomical Society in the UK. And I think that we're starting to make the first steps of progress here. So I hope that we can learn from the RAS examples.
Good, I'm glad you were there to field that.
So on a similar note, this is a question from Robert Massey. So he asks, it's in our UK satellite maker constellation radio working group, it wasn't clear that the satellite operators who attended it were actually aware of the problem. So he's asking, has this changed? Are the mitigation efforts of the satellite operators becoming more convincing? And we have Federico to answer this.
Yes, thank you, Andy. So, we have been having many interactions with the different operators, and at the beginning, it was kind of difficult because we needed to explain that there needs to be an awareness not only of the radio astronomy protected bands, but also of the fact that, as Lish and Harvey were saying before, that radio astronomy receivers are quite wideband, and if we have so many satellites placing beams and power at the radio astronomy sites, it can basically saturate our receivers. So we would not be even able to do observations in our protected bands. And this was some sort of a process to try to explain to the operators, because also they are not used to this kind of approach, because they normally work at the ITU and then fixing on the radio astronomy protected bands. But to make it short, I think the situation has changed a lot, and the interactions with, especially with SpaceX lately in the different workshops that you have been seeing, and well, everyone knows now that OneWeb has been taken out of administration, and they are now again starting to interact with the radio astronomy community. So we would say the landscape is looking good, but we still need to work on that. But we really believe that the way we need to do it is to work together, the radio astronomy community along with the operators, to find a way that both systems can cooperate as much as possible.
Thanks, Federico. So on this topic of mitigations by the operators, so we've heard from the session yesterday that a good mitigation for the optical astronomy concerns is to keep the satellites low in the sky. We have a question here from Masaki Hiromitsu, who asks, is there any difference in interference by low orbit constellations and high orbit constellations? So he mentions that yesterday we were told that the lower orbit constellations cause less effects on optical astronomy, but how about radio? And that's for you, Federico.
Yeah, so I think that as Harvey was mentioning before, what radio communication systems try to do is to establish a link budget, right? So they need to transmit a certain amount of power so that the signal gets to the receiver with a certain amount of strength, let's say. So if the satellite would be lower on the Earth, then they would need to radiate less power, but the level of the signal on the ground would be the same, because they wouldn't be radiating more power if they didn't have to. And at the same time, if they need to go further away, they would have to radiate more power to get the same level of signal on the ground. So not really sure if that would make a difference a priori, but perhaps more thought would be needed if there is the possibility of satellites not pointing directly at observatories, as we are proposing as one of the proposals we have, and we think about the side lobes of these satellites and how could they look like depending on the altitude. But to be honest, I don't think there's a straight answer to that. But the reality is that the power level that the satellite would emit would change depending on the altitude.
Thanks, Federico. And we have a related question in a way here from Mike Peel. And he asks, are the technical specifications for the satellites, band passes, out-of-band emissions, antenna beams, side lobes, etc., are they available? And has anyone confirmed that they are performing to spec after launch? That's for you, Federico.
Right. Yeah, so there are some technical specifications of most of these constellations out there. Band passes, out-of-band emissions, some of. There are informations about the beams. So perhaps if you want to do a very, very detailed analysis, the public information might not be enough, but there is a lot of technical information available. And the second part, and all of this information, the best place to find it is on in the FCC website. Basically, I think that's where everyone has been going to find this data, and also in the ECC report 271 There's a lot of technical information on these constellations. And the second part, if has anyone confirmed that they're not performing, I think it's related to the other question we were talking about before, is that if anyone has made a measurement of this yet. And the answer at the moment, I think, is not, at least up to my knowledge. But it is a very, very good question, because it's not only measuring the transmitted power in the intended band, but it's also trying to assess how the out-of-band emissions look like, how the side lobes look like, in order to be able to verify analysis. Because we can do analysis, of course, but the real verification of the analysis is under measurement. So yeah, there needs to be measurements of this.
Thanks. So this is an interesting question, and I was also wondering this myself, and it's about interferometry. So are longer baselines enough of a fix, or will the mega constellations also cause problems for interferometers?
Well, can I answer for at least a small array like the VLA, they will interfere. The array achieves immunity with increasing distance. So VLBI is much less sensitive than a smaller array like the VLA, where every telescope is within a few tens of kilometers. The problem with trying to use that is that the array may be in different configurations in different times, and so its immunity is not fixed, right? And any use of that has to be coordinated if it isn't absolutely protected. Thank you.
Thanks, Harvey. Okay, so we've got a few more minutes left. So this is a challenging question coming from Chris Lee, and so he asks, as with yesterday, we need to know what the red lines are. When is radio astronomy severely constrained in its day-to-day operation? It seems we have impacts in our protected bands, and this can be quantified for the various constellations operating at different altitudes. And we have impacts on the bands that we exploit passively, but we don't own. So this kind of opportunistic science loss will therefore be of less concern to regulators. So I guess the question is, what can we do about the observations that occur outside of the regulated bands, and how can we maintain the importance of this? Do you want to take that, Harvey?
Yeah, that's why we're here. The recommendations that we're making to COPUS are agnostic as far as frequency goes, right? We're making recommendations that apply outside our bands. It's clear that simply working within the spectrum management framework, the regulatory framework, is not going to preserve access to spectrum for science. This also includes passive sensing. As long as the only gatekeepers to space are the radio spectrum regulators, you're seeing an increasing number of bizarre collateral damages, externalities, negative externalities. You've got all the effects on optical satellite, on optical radio astronomy, OIR astronomy, because the radio spectrum regulators that are the gatekeepers to space approving these constellations, 100,000 satellites, don't have it within their mandate to consider all of the effects of these constellations. That has to change. The reason that we're here at this meeting as radio astronomers is to make these broader regulations and to try to change the subject of discussion, to preserve access to spectrum for science outside the narrow framework that is serving a limited purpose, but is not doing the whole job. Thank you.
Thanks, Harvey. And I can say from the session yesterday, I mean, we've made this list of recommendations that call for increased industry astronomy community collaboration and understanding of the requirements of astronomy, and finding ways to get more access to the technical data of the antennas so that we can know the impacts are. So, you know, yes, these are steps that we need to take forward. Okay, so we have a practical question in a way here from Ricardo Bustos, and he asks, RFI is critical for the detection of the cosmological 21 centimeter line signal at low frequencies. There is a strong signal from the Orbicom satellite system. Is it possible to coordinate with them about their signals?
I wish we had someone from Australia. I think we would need someone from Australia to discuss this problem. Federico, do you have any experience with it?
Yeah. What I would say is that the emissions from the Orbicom satellites are basically seen all the time through the side lobes of low frequency antennas. The issue of low frequency antennas is that they don't have so much directivity, right? Most of the low frequency arrays that I'm thinking of SK low, low far. This type of arrays are using quite broad antennas, right? So there you have one thing that you don't have is the directivity. Then you have the directivity when you do the array by summing all the different antennas. But also the difficulty there to try to use some of these suggestions that we have in our document is that because of the low frequency, the footprint of the antennas that these satellites are using are very, very wide. So, and they are not directive, right? So I don't think this is something that can work, at least in the way that we thought about it.
Okay, thanks, Harvey and Federico. So we're drawing to the end. So there's one final question, which is going to Kasiana, and then she can close out the session. And this is a question about sky protection. So the question is: the sky is important for all citizens. So what actions is the Spanish government taking to protect the sky for the whole of the country? And this is for Kasiana.
Well, thank you. The Spanish government is now working on a new law, which is going to be of national coverage. And the good thing is that this law is being iterated with many of us. For instance, we at the Institute are working with them, and other people like Madrid and other places in Spain, they are working with them. So this is still in the phase of being a draft, but it's expected to be a good law applying all over the Spanish territory. So yes, and I think this is something which is, I hope it's something that is also happening in other countries, mainly in the south of Europe. I think Italy is also working on something on that. Yeah.
So thank you, Kasiana. So I think that's our last question.
Mm-hmm. Okay. So I think we are getting almost to the end of the workshop, for sure to the end of today's meeting, which has been very, very important. A number of things has been discussed, a number of things has been said. And I would like just to remain to all of you that we need your help and your input. For that, in the next slide, you will see which is the the protocol, the procedure. We have been repeating this slide all over the week because it's very important for us. In this slide, we tell you that the documents we have been producing are available for all of you. Not only available, but we are really willing to have your comments that we need to have in order to improve what we have done so far. So using all the discussion during this week and the comment that you are going to give us, not only in the chat or in the question we have had, but also in this document, which is in the slide, we are sure we will be able to produce a better document to be presented and to be discussed in the meeting in the United Nations at the beginning of next year. I would like also to thank, not only on behalf of all the scientific organizing committee, which is listed in the new slide, I think. No, the new slide, please. This is just an announcement. I mean, we have been saying almost in the very beginning, and our Spanish Minister of Science and Innovation has emphasized that we still plan and we will love to be able to have a meeting, a Congress in La Palma next year, in April next year. So it will be, we would love to have a standard meeting with all of us seeing each other and having, being able to iterate in a system, in a way more personal. That will be, we hope that it will be in April next year. So be attended to that because we are sure that you will be interested in joining to the meeting. We count on you for that. And then just finishing, I think the next slide is the one with a huge list of names. This is huge, and they are all, it's important because, I would like just to remind you that all these people have been working since June, trying to produce the documents that you will be able to read, and it has been summarized during this week. So all these people are very grateful for you for being with us in this workshop, for all your comments, for the huge number of people that have participated, would tell us that what we are doing is important and is interesting for all of us. And so I think this is the end. So we all these people listed here, thank you. And in particular, I would like to thank Connie Walker, who is the leader of all this group. She has been the soul of this work. Although she's not here giving goodbye, she's in the background of everything all the week and since June. So Connie Walker and all of us are very grateful that you are with us, and we hope to keep contacting with you in the future and to have your comments.
It takes a team, Cassiana.
Thank you, Connie. That is all. Take care. Goodbye.